All right, welcome to another IAEI News Live. My name is Thomas Dimitrovich. Today's discussion is the fundamentals of the ground fault circuit interrupter, and it starts now. All right, so welcome, and hopefully you're having a great day today. Today I am actually at the West Virginia chapter of the IAEI doing a program with a few other great leaders in the electrical industry. And so this is recorded earlier, and hopefully we'll get some dialogue going on the ground fault circuit interrupter. Now, I don't care if you're using a GFCI receptacle or a circuit breaker. You'll notice those GFCI circuit breakers, most of them have pigtails, but beware, some of them do not have pigtails. They call those a plug-on neutral application type of device, and make sure you understand the way those go into the panel board from the manufacturer. But we're going to talk about the basic fundamentals of the GFCI, this life-saving product that has graced the National Electrical Code since the early 70s and has grown ever since, and I believe is making a significant contribution to electrical safety in residential, commercial, and industrial applications. So let's dig into the GFCI. All right, so I do have a couple things that I want to make sure that I cover before we get into this discussion. Bear with me here. All right. Okay, here we go. Now, the first thing, I'm speaking, what you hear, I'm not speaking on behalf of any organization. I'm speaking, anything you hear is my own opinion. Now, I sit on code making panels 2 and 10 for the National Electrical Code. I do not speak on behalf of the members of code making panel 2 and 10. I don't speak on behalf of NFPA or anybody else. What you hear come out of my mouth is my own opinion. So let's just get that set up for it. Now, I will tell you that membership has its value in the IAEI. I'm creating a series of YouTube videos on this channel, on this IAEI channel. And I will tell you that we will be having sessions that will be open to membership only. And most of those sessions are going to be with industry experts, elaborating more in depth on code requirements, maybe more in depth on the technology. And this is going to be a primer for those videos. So please make sure that you have a membership in IAEI and watch this video and then follow up to find out the other resources that we have available to help you with your depth of knowledge on any of the topics that we pick. This one is GFCI's, the ground fault circuit interrupter. Now, I will also say down below, there's a membership link down below. And also down below is a link to get your copy of the analysis of changes. These books that the IAEI puts together, they work very hard. They sit on each code making panel of the National Electrical Code. They represent the electrical inspectors on those committees, and they put together the analysis of changes books. And here's the key thing about these books. Very great resource for you, very important resource for you, because this helps you understand where the mindset is of the electrical inspector. And whether you are designing a power distribution system, installing power system components, whether it be a residential, commercial, industrial, the analysis of code, the analysis of changes for each edition of the National Electrical Code. This resource is your view into some of the background and understanding of the not only what has changed, how it will impact you, but also why it has changed. And it helps you see the inspector's perspective on these code changes. So important resources for you. You can get yours, and you can get back editions of these as well. So let's dig into the GFCI. The GFCI is a ground fault circuit interrupter. And I have to get my code book. Everybody should have their, this discussion, I'm going to base it on the 2020 version of the National Electrical Code. Now, my references that I'm going to read out of this book are going to be just simply some definitions, general definitions that typically don't change, because this is a primer. I want to help you understand some of the basics and the fundamentals around the ground fault circuit interrupter. This is a protection of personnel, this device. Whether it be a receptacle type GFCI, a circuit breaker type GFCI, these devices are your last resort. From a safety perspective, we don't think of the GFCI as the primary method of you providing protection. There are a lot of other steps that you should take before you start to rely on the GFCI. Again, the GFCI is your last resort. We want to de-energize the circuit should a person come in contact with an energized conductor or an energized part in the power distribution system. So we have to understand the basics and fundamentals of the human heart. We have to understand the basic and fundamental impact on the human body. That helps us understand what our limitations are with regard to the amount of current and the amount of time that I let current pass through the body. Now, as it says right here, the pickup point is 4 to 6 milliamps. Now, that's a threshold. That's a pickup point. Any current that is in that range or greater will have a device like this operate. So that tells you that this device has some way to understand the magnitude of current that is flowing outside of the normal path. So remember this, that when you take a single phase AC circuit, you have a black or a hot conductor and a white neutral conductor, grounded conductor. What goes out on that black wire has to come back on the white wire. What goes out on the hot supply comes back through the grounded conductor. That is a complete circuit. These devices, whether it be a receptacle or it be a circuit breaker, have to discern and understand what current is going out, what current is coming back, and make sure that the current that is coming back and going out are equal. If there's something different, if what is going out does not equal to what is coming back, then it has to be going somewhere else. These devices don't know if it's going through a human person, if it's going through a conduit, if it's going through a metal framing of an electrical piece of equipment. It doesn't know where it's going. It doesn't care where it's going. It needs to open fast enough to ensure the damage to your body is survivable. And as we're going to discuss, the history and the way the standards have been created have recognized that the condition of the human body, when we say it will prevent death due to electrocution, it will prevent your heart from going into defibrillation, we're talking about a healthy heart. We're talking about a healthy individual. That's why we always say these devices are your last resort. Now, what you'll hear us refer to these two as is a Class A device, and that gets back to the standards, the UL standards. We're going to talk more about the Class A device. The reference standard for the GFCI is UL 943. Now, I don't care if it's a circuit breaker or if it's a receptacle or if it is a inline in a cord, portable GFCI. All of those GFCI requirements can be found in UL 943. And we're going to talk a little bit about UL 943 as well. Now, this I'm going to walk through a little bit on. This is a circuit breaker, GFCI circuit breaker. I'm going to help you understand how this device operates and functions. And we're going to get up closer and personal with it as we understand the various parts and pieces to this device. But as you can tell, there's a microprocessor in here. You see a little green board. That big blue device is an MOV, metal oxide varistor, that's there to protect that board from surges. And it would be, if you think about surge requirements or the way we should design surge protection, we want various layers of surge protection. You want the surge at your service entrance to knock the peak voltages down to manageable levels that these types of devices can then knock down to even lower levels of magnitude to protect the sensitive electronics. So it's a layered approach and it works as a system. So we're going to walk through this and help you understand how these devices operate and function. Okay, so this is basically a little bit of a one-line diagram for a circuit breaker type GFCI. And you'll notice right here is the pigtail. Why do we call it a pigtail? Because it looks like a pigtail. Now that pigtail may exist as a pigtail, but it could very well be what we call a plug-on neutral device, which multiple manufacturers are offering on the marketplace. So you may find a GFCI circuit breaker that does not have this pigtail, but it plugs directly right in the back of this, plugs directly onto the neutral bus. But this pigtail is designed to complete the circuit back to neutral. And I'm gonna walk you through the one-line diagram of the circuit basically through a GFCI circuit breaker. And then we're going to compare this analysis with that same picture blown up. And I'm going to help you walk through the parts and pieces on an actual GFCI circuit breaker so that you can see the current flow. And we'll also talk about how the push to test button works. All right. So when I have remember the principle that this works off, that big yellow donut that's there, all those conductors, the hot and the neutral, go through the donut. So when I have a current that flows out to the load, it comes back through that same sensor. All of the current going out equals all of the current coming back. And what that sensor does is it sums those two. Whatever goes out has to come back. The plus and the minus, I should get zero current on the secondary of that sensing coil. The output of the sensing coil goes to an electronic circuitry. That was that green board you saw in the picture, which we're going to see again. And in that circuitry is quite often it's a microprocessor. It could be an analog type of design, depends on the manufacturer. That's the recipe. That's the secret sauce, so to speak, of each of the manufacturers and what they bring to the table and how they get this done. So each of these devices, the output of that will go into that electronics. And then inside of the electronics is a brain that has to say, okay, if the current that's coming out of this sensor is greater than 4 to 6 milliamps, somewhere in that range and greater, then I need to open. But if it's less than 4 to 6 milliamps, I hold those contacts closed and I let it deliver power. That's basically how it functions and operates. So you have a tolerance of 4 to 6 milliamps. If you have any inductive or any capacitive leakage currents and things like that, they give you 4 to 6 milliamps. That's it. Anything greater than that is going to open this circuit. So let's take a look at how the push to test button works. So if you'll notice up top up there is a push to test button. When the user presses that button, you'll notice that the contact is now made. Now follow that conductor from the hot through the donut to that, and then all the way through the circuit. It goes through the donut, through the button, down around the CT, and then back out to that neutral. So what have I done? I've injected a current through the sensor, and I put a test resistor in there because I know what the voltage will be at these receptacles. I know I have to exceed 4 to 6 milliamps. And when I press that button, I bypass the sensor. Because I bypass the sensor, whatever the current is in that circuit based upon the voltage and the resistance of that test resistor, I know that's going to be my difference. It has to be greater than 4 to 6 milliamps. That information will go to the electronic circuitry. The brain will determine whether or not there's a problem, if it's greater than the pickup points, and if it is, it tells the solenoid to trip the circuit breaker. That's the fundamental principle of how this works. Now, I'll show you a diagram of a 2-pole circuit as well. And the common question I get is, hey, Tom, I don't have a neutral. I've just got 2 hots and no neutral. If this was 2 hots and no neutral, if the current goes outside of those 2 hots to ground, there's no neutral, then you don't have that imbalance coming back over the neutral, regardless. As long as the current stays in the path. The moment the current goes outside the path, this is the condition that you get. And the circuit breaker will open. So I don't need a neutral for a 2-pole. And if I do have a neutral for a 2-pole, and we'll show you the diagram, both hots and the neutral have to go through that donut, the sensor. All right. Now, this is a close-up look at the internal of a circuit breaker. And furthest away from me on that end is what connects to the bus. And right here next to my head, the very top terminal is your hot, and the bottom terminal is your neutral. Remember, the GFCI circuit breaker is the only circuit breaker outside of an AFCI. Both the AFCI and GFCI, you will terminate your hot and neutral conductors on the circuit breaker. Other single pole, like this single pole circuit breaker here, this single pole breaker, I have only 1 lug, and that's for your hot conductor. Where does the neutral go? Straight onto the bar. But in the case of this GFCI, you will land both the hot and neutral, and you must land that pigtail on the neutral bar because of 2 reasons. One is it powers up the electronics inside the circuit breaker. I need my reference to ground so that I can power the brain in this on that circuit board. And it gives my current a path back down to the equipment grounding conductor. So that neutral pigtail has to be connected, else you have a very expensive standard thermomagnetic circuit breaker. Now let's take a look at the parts. This, on the very far side of this, is the mechanism with the contact. The contact in this circuit breaker right here is open. It is not closed. You'll see the gap down at the bottom. The gap is, I'll just do a pen. This is my gap. Okay, this is one side of the contact, and this is the other side of the contact. So you have that's the set of contacts which are inside of the circuit breaker. Now you'll also recognize that right here is an air gap that lets the gases escape from the circuit breaker. We call that the arc chute. Now, if you watched the circuit breaker basics video as part of this IAEI channel, I told you about the arc extinguisher and I told you about the arc chutes. The arc extinguisher is a device that you will see in larger circuit breakers. on your standard 15, 20, 30 amp, whatever molded case, especially your single pole and two pole breakers in a residential type environment application. They don't have arc extinguishers. I don't need them. But I do need to have an area for the gases to escape when we interrupt the arc, because you will draw an arc between that contact point and this contact point. So that's where the business happens. This is where all the activity goes down when we are opening the circuit breaker. Now, this piece in here in the middle, that is your standard bimetal. That handles the thermal and the instantaneous on the circuit breaker. So I have my mechanical operation that has the levers, the springs, and I have my bimetal that establishes my trip curve. My bimetal will heat and bend and drop will drop the mechanism so that it opens, or if the fault currents are high enough, it will pull in the lever and drop my latch and open my circuit breaker. So this is the business. This what's highlighted here is that portion of the circuit breaker which does the thermomagnetic protection, your overload and short circuit protection. Now, that right there that is highlighted is a standard thermomagnetic circuit breaker. That is a UL 489 device. This is a standard thermomagnetic circuit breaker. Those are the internals. And if I wanted to match it, it's sort of backwards, but because it's actually this way. No, it's not. It's that's right. So there's my contact over here. My contact is over here. I'll open it and close it for you. Now it's closed, and now it's open. All right, so there's my contact that just closed and opened. Over here is my bimetal. This connects to the bus. This connects to the outside. This is where my load terminal is. This is where my bus connection is. So it's the same deal as over here on this video, or on this image here. It's a standard thermomagnetic device. It has to pass all of the requirements of UL 489. Now, this is where the electronics and the brain take over. I need my sensor. Remember, we showed you the donut, the sensor that the hot and neutral conductors have to pass through. All hot and all neutral conductors, not the equipment grounding conductor. And that sensor, the outputs of that sensor go to the board, which tells the brain, which the brain will analyze and determine if it needs to tell the circuit breaker to open. All right. Now we're going to follow that same, we're going to follow the circuit through the circuit breaker from the beginning, from the bus. So from the bus, it goes through the contact, up through the bimetal, and this right here is a wire. This over here, there is right in here is a braided conductor. That braided conductor is on the lever arm that's moving, and it has to be a braided conductor that is carrying current, because it will move because your contact will move. So we need to have a flexible piece of conductor there, and we all use a braided conductor, bare copper. So that braided conductor will let the current flow up through the bimetal. Now, remember, go back to Breaker Basics. I did a Breaker Basics video. You can check that out. And we will either heat this bimetal and bend it, let the latch drop and open the circuit, or we will provide enough magnetic flux to pull a plate in and drop the latch and open the circuit breaker. And then we need to get it through this CT. I need to get the current through that CT. So how do I do that? I basically put another small conductor through here, and then the hot conductor goes through this sensor. We'll call it a donut. And then it goes out to the load. That is the path of current through a circuit breaker from the bus that it's connected to the load conductor that you wire onto the lugs of the hot conductor. Now, coming back, I land the neutral here on this lug. My neutral current will pass through the sensor. It all goes through this same sensor, and then right back out to the pigtail onto the neutral bar. So the neutral conductor has a very short path through the circuit breaker, but the hot conductor, the main current draw from the bus, follows the path that you see on the screen. That's basically the current path, but it's very important that this sensor, both conductors pass through that. And you'll see there's a red wire right here, and I believe there's a black wire in there somewhere as well, that basically brings the current output to this motherboard, to this circuitry, so that the brain can tell the circuit breaker when to open. And you'll notice right here, there's a red conductor and a black conductor, and there's a plate, and there's a coil around this plate. That is how it tells that circuit breaker to open instantaneously, as fast as it can, without an intentional delay, when this device determines that you have more than 4 to 6 milliamps going outside of the path. Now that's how a molded case circuit breaker works. Now the receptacle, remember, a receptacle type GFCI, you got a few things going on. The placement of this sensor, the placement of that sensor is critical so that you get both the load terminals, right? So remember, on a receptacle, you have line and load terminals. And in fact, on this one, it's never been installed. We have some caution tape here, and it says the load terminals under this label are for feeding additional receptacles. Miswiring can leave this outlet without ground fault protection. Read instructions prior to wiring. And then they do it in Spanish or French. I don't know. I can't read it. Read instructions prior to wiring. So that's basically what's on this label. So this is your line. This is the upstream. That's these terminals right here. That's up here. The sensor is in between. So this sensor right here, that sensor makes sure that it provides GFCI protection for what's connected at the hot and neutral load terminals and at the face blades here and here. So the GFCI protection is provided for everything that's connected downstream on the load terminals and everything that's protected on the face through whatever is plugged into the face of this receptacle. Make sense? You should always wire that load, the line side. Don't forget your equipment grounding conductor. Put your hot, your neutral, your equipment grounding conductor, and then you've either feed it downstream and provide protection. So you can use standard receptacles downstream of this because this is providing the protection. I have seen applications where in a garage, every receptacle was a GFCI receptacle. Now it's very nice of you, but it's not necessary. As long as if they are all fed from one GFCI, then all of those are provided protection. Why? Because of the way the construction is on this device. Make sense? And it works off the same principles. What goes out must come back, and it goes through the sensor. All the current that goes out must come back, and if anything goes outside of that path, 4 to 6 milliamps, it will open. Hopefully that helped you understand the face and how that works. Now, there's another device, which is your portable GFCI. It's a little bit different because a portable GFCI has to do a few things in addition. Because remember, this is a portable GFCI. There's a wire in front of it and a wire behind it. And the way this works is, again, on a similar application, it's going to be looking for the current going out and coming back, but it adds this circuitry with open and grounded neutral detection. So if there's an open neutral to the device, it has to be able to detect that. So this plug-in portable type of GFCI device has to go through additional tests as part of UL 943 to make sure that it can determine and detect problems on the wiring ahead of it, because it is external to the structure and could be jeopardized. That's how that works. Now, your 2-pole, and I'm showing you an L1 and L2 and a neutral, but if you have an application where you don't have a neutral, you just have 2 hots going to, say, a pull pump, the GFCI will still work. Why? Because all of the current will be going over the hot conductors. If it goes anywhere outside of the hot conductors, you've got a ground fault. That current is going elsewhere. This GFCI will detect it and clear the fault. So I don't need that GFCI in this application. I don't need the neutral in this GFCI application. I can have that neutral, and if I don't need it. I will always have a balanced circuit with the load because it can't go anywhere else, as long as the current stays in the path. Another common question we get. All right, now, GFCI fundamental principles, and I've said it multiple times. What goes out must come back. The current has to stay within the normal path. Not just the path, the normal path. Whoop. So current must stay within the path, and if it goes outside of the normal path, through anything or anyone, remember, the GFCI doesn't know that the current is going through you. There's no skin detection. There's no detection that it's a human body versus a forklift truck versus a wrench versus a squirrel or a chipmunk. If it goes outside of the normal path, greater than 4 to 6 milliamps, it will open. Now, another important thing is the amplitude of current, the magnitude of the amount of current flowing. Now, how do we think about a current passing in a circuit? Now, let's say that I can determine your impedance, your resistance value, and I know what the voltage is that's impressed upon you, and I know the impedance of the conductors. So I know I can calculate, as long as I know your impedance and I know the impedance of the circuit, I can calculate the amount of current that's going to pass through your body, right? Now, let's say that I determine 5 amps of current will pass through your body. When you're on a GFCI circuit breaker or receptacle, there was nothing in that picture that showed anything that would limit the amount of current that will flow through your body. What I am doing with a GFCI receptacle or circuit breaker is only limiting the amount of time that I let it pass through your body. So a GFCI receptacle or a circuit breaker cannot change the magnitude of current that will pass through you. If I calculate 5 amps will pass through your body, when you're on a GFCI, 5 amps will still pass through your body. It will trigger at 4 to 6 milliamps, but it doesn't limit the current that flows to only 4 to 6 milliamps. You will still see 5 amps worth of current passing through your body. I will just, or the GFCI device or circuit breaker will limit the amount of time so that your heart, your healthy heart, won't go into defibrillation. That's how a GFCI will work to save a life. Now, this is your UL 943 and your 1053. So UL 943 is what a GFCI receptacle is listed to. UL 1053 is what a ground fault protection of equipment device. Whoops. Ground fault protection of equipment, and I just downloaded 1741, and I want to make sure that UL 1053. I want to make sure that I have the title right for UL 1053. UL 1053 is ground fault sensing and relaying equipment. So this is the standard that will be used for ground fault protection of equipment. Now remember, ground fault protection of equipment is not there for personnel protection. It is, think of it this way. GFCI is set to open at 4 to 6 milliamps. So GFCI is a milliamp, 4 to 6 milliamp type of trigger point. Ground fault protection of equipment can trigger in amps. Think about on 23095, we have a requirement for services, 1,000 amps and above. Service over current protect device. If you have a circuit breaker, 1,000 amps and above, you need GFPE, a UL 1053 device. And what's the maximum pickup point? 1,200 amps. So you can have a ground fault protection of equipment device with a triggered set point of 1,200 amps. That's not going to provide personnel protection. That is going to provide equipment level protection. So now the pickup, now remember, the pickup in GFCI is determined by the standard to be 4 to 6 milliamps. What's that determination? That is the let go threshold. That's not the defib. That is let go threshold. So here in the United States, we think of a ground fault circuit interrupter, 4 to 6 milliamps. We're considering let go threshold, which means if you touch the conductor at 4 to 6 milliamps is the point at which you will not be able to let it go. If it's less than 4 to 6 milliamps, you will be able to let go of the conductor. But 4 to 6 milliamps and above, you will not be able to let it go. And I want to make sure that I clear that so that the circuit is de-energized so you can let it go. Now, European standards don't necessarily worry about let go threshold. They worry more about the defibrillation, which is a higher 20 to 30 milliamp type of pickup point. And the trip times are approximately 15 milliseconds on GFCI, but a GFPE device is not 15 milliseconds. In fact, GFPE, the way the standard is set up, 85% of the pickup level. So let's take a 100 milliamp device. I get my calculator. Let's take a 100 milliamp device, 100 milliamps device. It shall not trip at 85%. So that's 85 milliamps. 100 milliamps at 115 milliamps, it has to ultimately trip. Now, what do we mean by ultimately trip? Well, it doesn't mean you're going to go to get a burger and fries and come back a few days later and it's going to ultimately trip. It will trip. It has to trip eventually. 150%, so at 150 milliamps, it has 2 seconds to trip. And at 250 milliamps, it has 1 second to trip. So remember, GFPE is there. Now, this is your maximum clearing times. In some cases, we can program a faster clearing time. So this is your maximum settings. You can create a device that has dials that you can set to trip faster and at lower pickup points, if that's what you want. So typically, these ground fault protection devices, outside of, say, your 30 milliamp, like 30 milliamp, there's nowhere in the code that tells you 30 milliamps. But we have, the industry is pretty much standard on around 30 milliamps. So that is the pickup point. Remember, it's a pickup point, not a limitation. Anything greater than 30 milliamps, and if 30 milliamps is your pickup point, then you're at 115%. 1.15 times 30 is 34.5. 1.5 times 30 is 45. So 45 milliamps has to be at 2 seconds. But that's just, again, it's a maximum. That's not personnel protection, but what it will do is identify a problem in the system and isolate it. If you have a short circuit somewhere to ground, you're probably going to get more than 30 milliamps. You're probably going to get more than 100 milliamps. And that's going to trip. And in many cases, you'll trip faster than this, especially in a multi-case circuit breaker. When you have relays and whatnot, most of those come programmable. Now, this is the curve for your GFCI. Now, this up here is your heart fibrillation curve. Now, how did they come up with that curve? Well, that's research. That is years and years and years of testing and development to determine when the heart will go into defib. This is the threshold that UL has established for the UL Class A device. And down here is where the typical Class A device trips. Now you say, wow, the manufacturers went above and beyond to go that fast. In reality, though, when you look at these devices, whether it be a receptacle or a GFCI breaker, I mean, the sheer nature of it is such that it responds that fast. So there's no need to add the delay. Now, I could add a delay if, for example, you had a device that was downstream that would put, I don't know, say 200 milliamps of current over the equipment grounding conductor for a very short period of time. Might I, as a manufacturer, say, well, I'm going to pull this up here? Yes, I could. I could add that delay. I could, if I wanted to, match this line. I could have my device trip and add an intentional delay for all of these data points to let time or current to flow for short periods of time over the equipment grounding conductor, but not be persistent. But I would still be very, very, very far away from this important line, which is your defibrillation. So the area under this red curve, under this maximum permitted by UL for a Class A device, is the amount of time that a manufacturer has to play with. And the only reason that you would want to add any time is to ride through any unwanted tripping issues. You might want to address compatibility concerns with an appliance that might have a equipment ground fault for a very short spurt, or maybe have noise, some sort of noise that flows over the equipment grounding conductor. I can hug this maximum permitted line. I can hug this line here as close as I want to, as long as I don't go beyond it. That's the only wiggle room that you have as a manufacturer. So you might have a GFCI and say, look, I press the test button and it takes longer than what it used to. It may be that that manufacturer added time to hug this curve. And it might be that that time that's being added is to let the appliance downstream temporarily use the equipment grounding conductor for whatever reason, but not contribute enough to trip the device based upon the maximum permitted threshold, and definitely not enough to put a healthy heart into fibrillation. Now, these are the performance, the withstand environmental. If I looked at UL 943, I could categorize the tests into these three categories: a performance test, a withstand test, and an environmental test. From a performance perspective, I'm looking at leakage currents. I have to think about a high resistance ground fault. I have to think about the open neutral. We talked about that on the portable GFCI. I have to think about my trip thresholds, the 4 to 6 milliamps, and my time, that curve that we just looked at. I have to be able to detect that grounded neutral that's out in the circuit. I have to make sure that I don't trip falsely based upon types of configurations of the circuit. I've got to consider low resistance ground faults, abnormal operations, extra low resistance ground faults. That's your high fault currents. I have to think about normal temperature performance, reverse. What happens if I reverse line and load, miswiring? I need to detect that. If I repeated that, what about the operating mechanism? I got to think about the operating mechanism and the performance of the operating mechanism. I have to think about end of life. In here, you'll have the self-testing features. You have the receptacle temperature limitations and the auto monitoring functions. Those are your self-testing capabilities. With regard to withstand, I have to make sure that I can withstand a physical issue. If I take this receptacle and drop it on a desk, that can't leave it damaged. If I hit the desk in that manner, if I drop it on the floor, you don't want it so sensitive that you have to go buy a new one. Although I'd love for you to. But we run it through tests to be able to withstand how electricians and others will be using these physically in the field. I've got to think about voltage surges. And then most adverse conditions, dielectric capabilities, overload, endurance, short circuit tests, my surge currents, any abnormal overvoltages or undervoltages. And again, the mechanical endurance, push and test reset button. How many times can I interrupt the flow of normal currents when I'm pressing this test button? I got to be able to do that over and over and over and over. And then you have your environmental, your humidity, your RF, your corrosion, your spill. You'll have your weather resistant devices, the ones that we anticipated will have to be outside. You have a little LED on these devices. I've got two different manufacturers here. I've got a Cooper and I've got a, I gotta get my glasses just to give the guy credit. This is my Cooper or Eaton, and this one is Hubble, and this is a Hubble device. It says it on the tang. This one here says Cooper right here on the tang as well, but I knew it just because it's also on the back of ours, but I don't see it on the back of the Hubble. They didn't put it into the plastic. So two different manufacturers make their devices very similar, very similar. But they all have to meet the same standards. Now, this is your Class A versus Class C and Class D. Now, you're going to hear about this during the code change discussions, especially around the 2023 code cycle. You're going to hear about Class C and D. And you'll notice that the pickup point for a Class A is right down here around 4 to 6 milliamps. Okay, so that's your 4 to 6 milliamps. Look at your class C and D, picks up around 20 milliamps, 20 to 30 milliamps. These devices, from a European standard perspective, they, again, think about the defibrillation, but not the let go. So there's a little bit of a philosophical difference there. In the United States, we want you to be able to let go of the conductor. So if I had, say, 10 milliamps flowing, in the United States, that would open it in a UL Class A device. I'm going to say United States. A UL Class A device would open that conductor. A Class C and D you would hold on to it and not be able to let it go. But the thought process here is that it's not going to kill you. It's not going to put your heart into defib because it's below those thresholds. The 20 milliamp device and greater, that's when you get into the defibrillation. And that's a Class C and D device. So if you think about and think about how we get the Class C and D devices, we in many cases we pay attention to the equipment grounding conductor, the size of the equipment grounding conductor, the impedance of the equipment grounding conductor. There might be special provisions and requirements on the installation, so you always have to follow the manufacturer's instructions. But also remember, if it's in 210.8, it's a Class A device. Anywhere in the National Electrical Code where we say ground fault circuit interrupter, if you use those terms, ground fault circuit and interrupter, without anything before it, like special purpose ground fault circuit interrupter, if it's a GFCI, it is a Class A device, 4 to 6 milliamps. Now, you understand now that the basic fundamental principle of a GFCI is current, what goes outside of the normal path, it has to stop the flow of current. Now, in this case here, what I'm showing you is that the three pieces of critical information that are important for understanding the what do you call it, the amount of impact on the body. You have magnitude of current that will flow, the path the current will take through the body, and the amount of time that we permit current to flow. Now, remember that I can't control necessarily the path. I mean, nobody intentionally says, I'm going to touch this with my elbow and I know it's energized. No. If you're touching something that's energized, you're not doing it on purpose. So you don't necessarily control the path that it takes through your body. I can't necessarily control the amount of current that flows through your body. The only thing that is in these three parameters, the only thing I can control is the amount of time that I let the current flow. But I have to be able to determine that the current has gone outside of its normal path. Now, 4 to 6 milliamps. Okay, so these tables that you see here, we have a lot of research behind us as an electrical industry that helps us understand this table. Now, there were a few players in the history of the electrical industry that helped us determine these. We're going to talk about those. But what we know by this table is that anywhere from 0.5 to 3 milliamps, you're going to have a tingling sensation. From 3 to 10, your muscles will contract and you will have pain. From 10 to 40 milliamps, that's your typical let go threshold. We talked about it. 30 to 75 milliamps, you have respiratory paralysis. Then you get into ventricular fibrillation. Then you get into heart clamps tight. And you get tissue and organs start to burn. Because current will pass through your body. It's going to go through your veins because that's your that's the salty solution. That's the low impedance paths through your veins. They're like conductors, and your veins go straight through your organs, and they can damage your internals. So this table, if you think about it, I mean, I don't want to touch a conductor. Why do I care if I'm going to get a tingling sensation or a muscle contraction and pain? We want you to understand the severity. We want you to understand that you may not have any control. It is an unforgiving technology. It is an unforgiving thing. Electricity, touching electricity, you can't see it. You can't smell it. But once it starts passing through your body, you may not be able to let go. You can have ventricular defibrillation issues. Your heart can clamp tight. You can burn internal organs. It's important to understand the impact to the human body. You don't want to see videos of it, and you don't want to experience it. Now, another important part of this is to understand the impedance. Now, you know, in all of your 70E training classes, you're going to see this. You're going to see the previous table where we talk about the impact on the body. And you're going to see this because we know the amount of current that flows through the body is based upon your impedance of your body. And your finger touch, 40,000 to a 1 million resistance, ohms of resistance. And when it's wet, it goes down to 4,000 to 15,000 ohms. Your hand holding a wire, 15,000 to 50,000 ohms dry, 3,000 to 6,000 ohms wet. The basic message here is that the impedance of your body, you know, your skin is relatively a large resistance, and everybody's skin is a little different. Some people have calloused hands. Some people have very soft hands and soft skin. And it might not be just your hands. It could be the back of your hand. It could be a very soft skin. You're not going to have calluses on the back of your hand. Unless you're a teacher and you do a lot of that, right? But the main message here is when you perspire, damp and moist skin lowers the resistance of anything because you've increased the conductivity. You've lowered the impedance of the circuit, and you've lowered the resistance. You've increased the amount of current that can pass in the circuit. So all of our electrical workers perspire when they're working, I'm sure. Your skin is no longer dry. It's going to be damp. That lowers your resistance, and it increases the amount of current that will pass through your body. Now, we know all of this stuff because it goes. I've done my research on this one, and I'll tell you what, there's IEEE papers, there's magazine articles. I found this one. This is a UL study that was done in 1939. Electric shock as it pertains to the electric fence. What was going on back in the 30s? You've got farmers who get electricity into the barns. They're powering lights. They're powering blowers and fans and motors. And someone said at some point, hey, I wonder if I put a couple of light bulbs and I run a wire around an area, I can keep the cattle in because I can reduce the current. They'll feel a tingle if they touch it and they'll move away because they'll go, whoa, and they'll never come back to that area again. And they'll become very well aware that, hey, when I touch this fence, I feel pain. And so they will stay in an area as opposed to barbed wire. But the problem with it was children and others would grab the fence and become electrocuted and killed. So somebody came out with an idea for a new product. And this is how all of this stuff works. We're seeing this with power limited circuits, right? In the 2023 code cycle. Somebody says, hey, I've got this new pulsed power. And that's what this was. This was pulsed DC for keeping in cattle and lambs and pigs into an area in farms. And they said this won't kill a person because it'll be a pulsed DC signal and I can stop the pulse. So, and this was in the 30s. And that manufacturer made the claim, but then UL had to say, well, will it kill somebody or will it not kill somebody? So they had to do testing. And the testing that they did, they tested on adults, they tested on children. They had to determine the impedance values of a human body so that they can establish the curves. They tested, they know what it did to hearts because they tested on inmates who were on the death, on the electric chair, died in the electric chair. And they tested on animals to determine when a heart would go into defibrillation. And they came up with all the numbers that we use today. You would never be able to do that testing today, but we have those numbers based upon what they learned. And then Dalziel came along in the 60s and said, hey, now, we have this electric fence that's out there and it's got a UL standard and everybody's buying that and they know it won't put your heart into defib because of how it operates and functions, because of what we learned in those studies. And then Dalziel said, okay, I'm going to do some more testing and I want to understand let go thresholds. So they performed testing. They would put an electrode on your band around a person's arm and they would hand them another electrode and they would pass current through this portion of the body and they would watch the muscles contract. And until they found the value of current to where when they started it, that the subject would be able to let the probe go. That became our let go thresholds, 4 to 6 milliamps. We established that. And I would argue that we had actually established that in the 30s. Before Dalziel did this, Dalziel continued the research at various frequencies, no, mind you, and determined the let-go thresholds. Published it in IEEE Spectrum magazine, Electric Shock Hazard. That was in 1972. Remember, GFCIs went in the code in 1971. Around swimming pools, I believe it's what it was. You got to stay tuned for the program on GFCI and the NEC as part of your IAEI membership. So remember, we cannot control the magnitude of the current flowing in the human body, but we can control the duration of that we permit the current to flow through the body. We can't control the path that current takes through the body, but we can control the amount of time that we let current pass through the human body. All right. Now, that was basically gives you a basic fundamental understanding of a GFCI, whether it be a receptacle or it be a circuit breaker. Now, some other tidbits of information. This circuit breaker here, this is a circuit breaker. This is actually a see-through circuit breaker, but this is a GFCI circuit breaker has to pass UL 943 for GFCI, but it also has to pass UL 489 for thermomagnetic circuit breakers. So it's not like you just have a UL 943 device, you have a UL 489 device circuit breaker, and it also has GFCI, which is listed to UL 943. Receptacles. Your receptacle is listed to 498. And it'll be a 498 device because it is a receptacle. It has to pass all the tests of being a receptacle. And in addition, it has to pass the tests of UL 943. So these devices function to provide GFCI protection. Do I need a neutral? Do I need an equipment grounding conductor? No, I don't. Remember, I don't need an equipment grounding conductor. I don't need a neutral. On the load side of, say, a 2-pole circuit breaker, I have a hot and a neutral, obviously, for my circuit. But if I have a 2-pole device, I don't need a neutral. I don't need an equipment grounding conductor because all I'm looking at is the hot and the neutral. I don't care about the equipment grounding conductor, whether it's there or not. If you come in contact with it and it passes through your body, that means it's going to find its way back to the source without going through that donut, the sensor. And the same philosophy applies to this receptacle. What else? What else? I need the pigtails. So don't install these devices and not land the pigtail. The pigtail will fire up the brain. Another common question is, how do I test these devices? I'll get a question of, I used my indicator. I used a GFCI handheld test device and it didn't trip my GFCI or AFCI. The way to test any of these devices is to press the test button and press the reset button. That's the way to test these devices. Don't rely on any third-party piece of equipment. What those third-party devices are there for is if you have, remember, these devices here, I can have downstream of this, I can have all standard receptacles. Downstream of this, I can have all standard receptacles. I'll tell you, in my in this house here, I don't have any GFCI receptacles in my house. I have GFCI in my circuit breakers. Now, if an inspector came here when I'm selling it, and they went to my bedroom or my bathroom and they went into my kitchen, they would say, you don't have any GFCI receptacles. And I would say, that is true. My GFCI protection is offered in the circuit breaker. Now, how do I know whether or not which receptacles are on this GFCI protected circuit breaker? How do I know which receptacles are protected by this GFCI receptacle? I can do one or two different things. I can use that test indicator and plug it into a device, press the button, and watch it trip the GFCI. And if it doesn't trip the GFCI, does that mean that that is not on that receptacle? No, not necessarily. There can be a problem with your tester. There can be a compatibility problem between the tester and the GFCI receptacle. Excuse me. What's a great way to test it? Press the test button. De-energize the circuit. Then go to your load, what's being supplied. Go right here to the face. You shouldn't power anything up. Get a lamp. Plug it into the face of this. It shouldn't power up. Anything that is supposed to be on GFCI protected, plug that lamp into those receptacles. If it doesn't power up the light, it's not energized. You can use a meter, a digital meter, and test the receptacle through the blades. There are multiple ways that you can test whether or not a receptacle is being protected by one of these devices. So don't rely just on that handheld unit, is my point. I've gotten many phone calls where I've, and some of them, the handheld unit was broke. And an inspector was going to reject everything. And the electrical contractor would call me and say, hey, how do I get out of this? Because I think he thought it was his tester. And I said, well, go to the receptacle that you know is protecting it and trip it. And then plug something in downstream and show that inspector or show the homeowner it's not protected because this is open. And then close it, power it up, plug that light back in. Now you've verified presence and absence of voltage. It's no different than testing for absence of voltage from a 70E perspective. Again, remember, if you're powering a pull pump and you have a 2-pole breaker, you don't need the neutral. You can use 2 hots. If you don't have an equipment grounding conductor, you just have a hot and a neutral in an older home, these devices will still work. I don't need an equipment grounding conductor. And I think that's just about it. So remember, please subscribe to the UL channel, subscribe to this channel. All right. Don't forget to subscribe to this channel. Don't forget to become a member of the IAEI, because I'm working on materials that will be available only to IAEI members. What you're seeing here are fundamentals. These are starters For more detailed technical discussions to follow, more often than not, those are going to be available to IAEI members only. So please join IAEI, subscribe to this YouTube channel. If you're not following us on Facebook or LinkedIn, get over there, get engaged. Send me your input, send me your feedback, send me what you want to talk about so that we make sure that we provide the information you're looking for. Hopefully you found this technical session of value to you. And remember, this is brought to you by the IAEI, great organization you need to be a part of if you're not already a part of it. You need to be engaged. If you're a part of it, of that network, you need to get engaged, step up to the plate, assume a leadership role in this organization, voice your opinion, share your thoughts, and get involved. Get involved with your local chapter, get on the board, help board members succeed. Tell them you want to be next in line, to be engaged, to be involved. Help them put together educational materials. Help them find sponsors for events. Help them with their venues. Volunteer, share what you know, and help the electrical industry grow. All right. Thank you for joining us. Thanks for your time today. Remember, be safe. Thanks for what you do for the electrical industry. Thanks especially for what you do for the electrical safety. Be safe, and remember, stay healthy. Until we meet again next Tuesday, this is Thomas Dimitrovich signing off for IAEI News Live. See you next week.